There's actually a whole bunch of examples with the Acumen distribution. There's in particular, in relation to the previous talk, Mark's talk, there's one example called number 6 multiple examples in one file that has at the very, very end a model of a quadcopter that had been used to explain some ideas in one of the files. So if you run the last part of the animation, then you'll also see it in flight. And as you can expect, the model looks a lot like what you might find in a paper. In fact, this particular one, I think, is taken from a paper that somebody else had written. So this is just a small piece of information to connect to the last talk. Okay, so going back to our presentation, the plan was not the very beginning of the presentation, maybe skipping a few slides. Oh. All right. So yesterday, no, that's not the one. Sorry. Oh, okay. This it's a little bit tricky to browse this way. So here we go. Here we go. That's, I think, the one that I want. Yeah. So we started talking about physical form and how to model it, and abstraction, simple abstraction and instantiation of models, and presented an example with the car of elementary dynamics and control. And then we had this small bit at the end where when the car gets to 20 meters or a certain position, it starts braking. And we use this to illustrate what would be hybrid, what can be considered to be hybrid dynamics. Of course, the quadcopter that can close back its wings, like we saw in the previous talk, is an even more sophisticated example of hybrid dynamics. But the key point from our point of view here today in the modeling discussion is that hybrid systems are perfectly fine modeling all kinds of situations, whether they are simple or more involved. They're very good for doing that kind of thing. So now we'll talk about discretization and quantization and briefly mention this interesting behavior that happens, or one of the interesting kinds of behaviors that happens when we combine continuous and discrete together in one modeling formalism, xenobehavior. I'll briefly talk about enclosures, which are a kind of a verification technique that's very similar to simulation, but is a formal method. And hopefully, if there are some examples that you would like to talk about, maybe we can talk about them briefly as well. So to get into the discussion of quantization and discretization, let's go back to our model. So I think I had saved it as just need to locate it. There we go. Oh, no, actually, new models. Day 2. Okay, so this is our model with the two cars, the red and the blue car. And we can run it again to remind us of basically what it's doing. And this is the basic story that we are looking at. And if we look at the plots, we get a little bit of detail where we see here, this is the position of the first car. This is the speed of the first car and the acceleration, and then the position of the second car, the speed of the second car, and the acceleration. And you can see that in the acceleration there's quite a difference, and this one is the z variable that compares the two accelerations, the two positions, I think. Yeah, exactly. So z here is equal to x1 minus x2. All right, so where does quantization or discretization come in? They're essentially the same thing. We use discretization to talk about what we're doing to time, and quantization to what we're doing with values. If we're looking at the position of the car in front of us, and we're implementing our controller in a discrete system, in a computer, then we don't do that continually. So we don't have the ability to really realize an equation like this that affects the acceleration. So what we do is we're going to introduce a notion of a clock, and we're going to see that this is easy to do in a hybrid system, and we're going to use this clock to do sampling. And we're going to see the effect of all of this on our control system. So the way we do that is we're going to say, okay, we're thinking here of the second car, and we're going to introduce a timer, let's call it T2, initially equal to 0. And we're going to have a derivative for this timer for a reason that will become apparent shortly. And then, in fact, let's just do that and see what that does to our state. So the way we're going to introduce the timer is we're going to say that if x is less than, or if x is greater than 0.1, once we reach 0.1, we're thinking here of, T2, and 0.1 is the period that we're thinking for doing the sampling. Yes?
Can you please enlarge the text in the editor?
All right, good suggestion. Is this better?
Yeah.
Great, excellent. The PhD student that is responsible for introducing this feature is the person to thank here. But, I'm glad we can do it. So if T2 is greater than 0.1, and we're taking 0.1 to be the period of the sampling, then what do we want to do when that happens? We want to do a couple of things, but for now we're just building a clock and we want to see what that's like. So we will just reset the counter, the time counter. Else, we will simply have T2 prime equal to 1. And what that means is when we're haven't reached this value, then we just want the value to increase. So let's run that. Nothing special happens to our simulation. We don't have any connection to the cars yet, but we actually get this thing at the top here. And it starts at 0. This is the T2 variable, and it starts at 0, and when it reaches 0.1, it will have a value of surprise 0.1 because the gradient is 1, the slope of this line is 1, and then it will trigger this event when it's slightly over 0.1 that gets it reset to 0. So this gives us a way to have an event that happens every 0.1 seconds, roughly. Yeah? Great. Now, what do we want to do at that point? We want to model the fact that we're not seeing the exact position, but we are observing this position at a particular time. So what we'll do is we'll introduce another variable and say that we have x1 estimated, and initially this is 0, and use that also in the same kind of if statement. So basically take x1 estimated to be equal to, what should we set it to be equal to at this point? During the sampling, we can take x1 estimated to be just x1. Yeah?
Excuse me.
Yeah?
It is a new kind of syntax because it's plus equals to.
That's exactly right. So this is used to indicate that we want to do this just instantaneously. And the main thing that it allows us to do is it allows us to be able to refer both to the old value of T2 and the new value if we need to. Yeah? So we're going to assign a new value to T2, but if we use T2 in the rest of the expression, we can still refer to the old value, because a lot of times that's a very useful thing to do. Yeah? So plus equals is the discrete assignment or the jump. That's very good. So then if we run that, we should be, again, not very much is going to be observable on our system, but now we have this new x1e variable, which is this one here. And it looks a lot like x1, but you could see that if we zoom in, it has these discrete jumps. It's not going kind of as smoothly as the other one. Okay? So now, so far, we are just sampling, but we're not using this in our control. So how do we model that? Well, the way to do that, so far it's been easy to introduce a clock and to do the sampling with this if statement. In order to have the sampling be done, to be used, we can do this in a couple of ways. The easiest way is to go here in this equation, which says minus 100 times x2 minus x1 plus 10 times x2 prime minus x1 prime. We can go here and start using x1e, the x1 estimated. Yeah? Now, we can expect to see a difference between the original curve that we have here, and the other, yeah, so actually try to keep a picture of this in mind, and we can even see what the maximum overshoot is. We could, if we want, make 3 cars, one with the quantization and one without the quantization. In fact, let's do that. Yeah? So let's go here, and what we'll do is we will introduce. The easiest way to do this would be, well, okay, let's make a new car. Let's call it 3, and let's make it, what is a good color for the third car? What's that? Green. Okay, it's going to be the green car. All right. And then we'll also need some variables for this car. And I'm going to confuse myself a little bit, but you guys are going to help me now, right? So these guys are the same, and we probably want to put this somewhere else, so we'll put this at -2. And I'm going to pretend that the one that I'm doing quantization for is the third one. And then, okay. All of our models are here. So I will just copy this without change and make this. Yeah, we'll need to make one more small change. So we're going to copy x2 equations here and keep them as they are. And then let's call this as z12 so that we don't get confused by which z it is. Yep. And then we call the new one 3. And 3 is going to refer to itself. And maybe start with this without, let's do that. And this is a lot of changes, but hopefully it will be okay. And this is going to be 1, 3 if we want to be consistent. Does this work? No, of course not. All right, I'm missing a comma. Does this work? And it says, wait, I don't have this z13. I haven't seen it before. Okay, and it's right, of course, we need to make that 1. And then it says, I don't know what T2 is. Well, it's right about that, because now it's called T3. I think. Let's try that. Whoa, it works. And 3 cars. Yep. And if we want to see what's going on here, you can see that there's a little bit of a difference. The green one with the quantization of the sampling is going a little bit slower. And if we look at the curves, we're going to have, this is z12 and z13. The default order for putting the variables is alphabetical or lexicographic. So we have z12 and z13 at the very end. And you can see, in fact, that the errors when we start quantizing are very different. And here, there's a very strange effect. There's some very strange effects that are showing up in different parts of the system. This is the acceleration. This is the equation that we changed to use, changed x1 to x1e. So this is x3 double prime. This is the acceleration of the third car. And what's going on here is really interesting and kind of dangerous to have in a real system, because you see that the acceleration is swinging from -31 to +30 or to +50. These are very big accelerations. What's going on here is fortunately something a little bit that is artificial because of the way we modeled things here. Because usually you don't have once you start modeling the quantization or the discretization of the sampling, you don't have the equation sitting there being affected all the time. You don't do the controller in an analog way. Actually, if you did the controller using an analog circuit, maybe this is what you get. But that's not usually what you do. What happens in particular is that this equation gets updated when we do all the updates. So it should really be in the if statement. It shouldn't be changing all the time. So here, the equation is affected by the change that happens to x1, but then it also is affected by the change that happens to x3 and x3 prime. Okay? So we kind of really want to have these things, this equation move inside. So the way we're going to do that, there's different ways to do it. Let's just say control 3 is initially equal to 0, we use another variable and go into this loop here and say that control 3 plus equals this equation here. So this way, the update happens on the clock ticks. And if we run that, it says something is not quite right. I can't spell. Now we have our cars going, and again, you see this green car is a little bit behind the blue car. But things have smoothed out a lot, mostly because the signal for the acceleration is being updated at discrete times. Okay, so the signal, the discretized signal for the acceleration, maybe I can blow up things from, this is car 3 and this is car 2. So if we look at just car 3 and car 2, and this is the discretized, or the acceleration with the sampling of the inputs and the sampling of the update. And then this is the one without, this is x2 prime. You see that actually this looks kind of close to this one. The main thing is that it is only happening at discrete times. Okay, so this is a more reasonable model, and things actually don't look too bad. The only thing that's significant is we get this kind of like accumulating, these are the errors compared to where we want to be. And here the maximum peak is 0.1 approximately, whereas here it's 1. So the green car, if we look at it, it looks like it ends up being potentially up to a meter behind of where we want it to be. Okay, so we get an accumulation of the error that's a little bit too much. So this is something to keep in mind about what happens, or some of the things that happen when we go from the continuous models of the control and the dynamics to the discrete or discretized model of the implementation of the control. There are many different approaches to dealing with this. The most important thing that we're trying to do here is to show that when we're modeling, we could use these models to understand, to see the effects of these things. Okay? And then we can understand the need for things like discrete control systems, discrete time representations of control systems, and other ways of dealing with these things. Yeah? So this is discretization. Do we have any ideas for what we could potentially do to deal with this, or is there something else that we need to do to make this more accurate as a model of how a controller would work?
Adding a time delay.
So adding a time delay is a very good point. We do get a kind of time delay effect automatically when we sample only at certain points. Yeah? So the updates basically become a delay. We could, if we want, also add additional delays. That's something that we can definitely do. Yeah? If we hold on to that thought for a bit, is there anything else about this equation that maybe we can make more realistic? So yeah, Martin?
We could deal with the saturation of the control outputs.
Yeah, so we can have limitations on the control output. That's another really very good thing to do. And in particular, if we look at the accelerations here, we notice that here we have an acceleration of 10. Yeah. Now, if you have a real car and the coefficient of friction is not exactly at 1, you might have, since gravity is about 10, you might have a lot of difficulty realizing that. So your cars might skid. So then we can model that also using an if statement, actually. Yeah. So delays we're going to get to, I'm thinking of something that would get us to delays very shortly. The saturation is something that we can deal with an if statement. The thing that I had in mind here is we are using x3 and x3 prime liberally because we're pretending to be the third car. Yeah? We've said that, well, we're not the first car, so we need to do something external and have an estimate of that somehow. So that's why we call it x1. But we're also kind of pretending that x1 prime is readily available, the speed of the other car. We're not sitting in the other car, If we're in a platooning scenario, we can actually do really interesting things like have the one car send us a message via communication channel, say, hey, here's my speed. Now, of course, we have to trust that, and it has to come through. Yeah? But it's not, x1 prime is not something readily available for us. And we may actually be interested in knowing the acceleration of the other vehicle as well. So when we're platooning in a sophisticated system, one car can send this kind of message to the next car and help in improving the performance. So what I'm thinking about here is that we kind of really need to estimate the speed. So how do we estimate the speed? I'm in one car. I only know the position or an estimate of the position of the other car. How can I estimate the speed? Any ideas? Divide by time. I heard that one. Okay, and I heard store. So divide by time, store. All of those things come together somehow. So let's try to do that. And tentatively, we replace x1 with x1 speed estimate. Yeah? And we need to declare this eventually. But if we go to what you guys were saying, we're going to need to say that x1, we want to say that x1e is something minus x or x1 minus something, yeah, divided by, what are we going to divide by? This guy here? The same period, yeah. Now, we need this other something, so let's call it x1e old. I know that my variable names are very creative, but bear with me. x1e old plus equals, what is this going to be? This should be the old value of x1e. And this is a place where this plus equals is useful. So here we refer to the old value of x1e, and here we're saying after all of this in this particular part of the program is evaluated, update the x1e with a new value. Yeah. Okay. So the only thing that we need to do in addition to this is to declare this x1e, x1se, sorry. And we'll take that as initially 0. Let's see if that works. Of course not. It doesn't work. Why doesn't it work? x1e variable is not declared. Aha, we need to declare that one too. So x1e old is also initially equal to 0. Try that. Am I still missing?
You wrote 0 instead of old.
Ah, okay. Thank you. Okay, starts to work, or at least something seems to work. So where's our new variables here? x1e is here, and then x1eo is right after it. And if we zoom in, hopefully they're one step behind. Yeah, okay, so this looks at the transitions. This value here becomes this value there. So this is going in a good direction. And then if we zoom out, we would like to see the x1se. And wow, all right, so here's the x1se, and it kind of looks like the x1 prime. So that's a good sign. Now we go to the rest of the signals, and here's the new acceleration signal when we're taking this estimate into account. But guess what? This is the current, the latest version of our error. So x1e has changed when we did this. It looks, you know, do you remember what it looked like before we did this change, before we estimated the speed? Yeah? So it looked like something like this. It went up here and then started to go down. And this peak was 1. And now this peak, if we look at it, is 0.4. Is that better or worse? Well, if we want less variation, less error over time, yeah, that's maximum error, let's say, then this is an improvement. It's kind of a little bit surprising, but when we started estimating the speed as opposed to using the speed, somehow this improved things. And the interesting thing here is we're using, if you remember the equation for a controller, we're using these speeds for dampening. And somehow this has affected dampening, but in a good way. So when the estimate for the speed was done kind of in a consistent way with the estimate for the position, this has actually helped things a little bit. in this particular case. So this is not something to take generalizations from, but all of these things are just illustrations for the kinds of things that happen when we introduce discretization. Yeah? All right. Did you catch how we did the delay?
No.
Okay.
Because I thought more in a way that, like what you mentioned before, where you transmit something from one car to another car. So basically transmit information,
Yep.
adding there a delay.
Yep. So this is the thing that I was pointing to. So this is X1E and X1EO, which is the old E. So the X1E old is just one step behind. So whatever value we have here, so let's say X1E has 0.8, and then we go down, in the same place it has 0.4. But then in the next cycle, it has 0.8.
Yeah.
So we do that in the same kind of loop that does the clocking and the sampling for us. Yeah.
So you just keep the old value for one tick.
That's right, exactly. So it's very much, these plus equal things are very much like difference equations. So it's almost like defining xn plus 1 in terms of xn, for example. Yeah? Cool. All right, so we got the discretization. What is quantization about? The basic idea of quantization is if we look at something like the speed again, which we're estimating, and we look at the actual value at a particular time. So this says 6.63, and it has a lot of digits. But these digits are not necessarily very meaningful for a number of reasons. One is that we may not be representing these kinds of values using floating points. The other is that often there is noise and imprecision, and limitations to the accuracy that we could use for these things. So one way to represent that is to say, well, we just do rounding, we do quantization. And the place to do that is when we take the reading when we take the sample right here, when I look at X3's estimate of X1, I can just say round. This is the rounding function that takes a floating point number and just takes the integer part of it. And I could just run that. So look at this value, X1E, which goes kind of smoothly here. If I only have a kind of a limited precision, then what's going to happen is these steps are going to be only integer valued. And I can vary this. I can use the round function or something like the round functions to pick whatever level of quantization I'm interested in. So let's say, for example, that I want to use not integers, but fractions, 0.1 fraction steps. How do I do that?
You multiply by 10 the value inside the round, and
Perfect.
then you divide.
So this is the trick. Take 10, multiply it inside and divide it outside. So it kind of shifts the decimal place. And I could do that for whatever level of precision that I want to use. And if I look at that, well, okay, now it's a little bit more. I can look at my numbers here, and they go in terms of steps of 10. They should. Ah, here we go. I just picked one that wasn't. Okay, we can also make it less precise, but notice what happened is once I start doing this, even with a limited amount of quantization, look at what happened to our error function at the end. Yeah? So you see now we have vibrations that continue for a longer time in our system. So this is another source of, in a way, noise or instability, disturbance or instability that comes into the system when we have finite representations. And here, things can look pretty tricky. Interestingly, if it's big, it can also end up quieting down some of the noise effects. So what that means is you may have a system that seems to be doing just fine. You've implemented it, and it seems to be doing just fine because at the end of the day it started to behave in an acceptable way. But then you reduce the rounding and it starts having more problems. Okay. Now this system, as we see here from this visualization, is not really doing just fine in this particular case. It's jumping around. Yeah? So if we put back if we increase the precision of the representation a little bit, we see that this comes back. Hopefully improves a little bit. Yeah? So this vibration oscillation behavior winds down a little bit. Okay, so we're not going to look, since we're looking at modeling to be able to understand effects of things that are going on in the system, we're not going to look at all kinds of solution techniques. The right place to look for how to solve these kinds of problems is to look, learn more about control. So this is kind of the role of the simulation and the modeling tools, is to help us make sure that we understand what's going on in the system that we're designing, and then to look for solutions. We're not necessarily, the tool is not going to solve these problems for us. The tool has the role of letting us know that there's something that requires attention here. Yeah? Good. So this is basically all I want to say about quantization. It's an open challenge for all of us to explore, kind of suggest ideas for dealing with these effects. Yeah? Things that we could do include doing things with the gains, thinking about other ways of doing feedback. Let's see how you guys come up with possible solutions for this. Yeah? You could, of course, learn more about control, but you don't need to do that. It's an open challenge. Okay, so let's stand up. We're halfway through this lecture. Take a break. And I suggest that in pairs, we kind of talk to the person next to us and discuss briefly what we think the most important development in CPS over the next 5 years could be. Yeah? So just to change pace. So let's get up, stretch, and take a couple of minutes to do that. A lot of information.
This material on active learning, but
All right.
Too much of the set. Crazy. More crazy than me.
Thank you.
All right. So we had a very nice discussion, me and Martin, and we think that biological and intelligent cyber-physical systems, like the brain, for example, will be very interesting areas for development in the future. So that was our discussion. I hope that all of you had good discussions as well. So leaving behind quantization and discretization, we go back to this business of Zeno. And it's something that happens very naturally in a lot of different situations, such as mechanical systems. What you want to think about is any dynamic where you're going outside a boundary, and then you hit this boundary, and as a result, you're pushed back. But then the natural dynamic is still pushing you out. So then you get this bouncing behavior. And we can illustrate that with a simple ball that falls from a distance and then bounces. So we'll do that with a model without any graphics because the plots are very easy to follow. So let's say we have a ball with a position and acceleration. Actually, it's good to have some height for the ball. And then say if x is greater than, if x is kind of hits the ground, and this is a kind of a practical simplification, and x prime is going down, then we want the speed to switch around. Maybe it will be twice as fast as what we started off with, but it will be in the opposite direction. So this is the idea of bouncing. Is this clear to everybody? Yeah? Very simple model. So what do we expect to see here? Ball bouncing. Good. All right, let's do that. What did I do here? Algebraic loop. That's the right semantic. This is a little bit surprising for me.
But it happens quite common when you model several physical systems that you run into algebraic loops.
That is true.
Yeah, that's nice.
Aha! This should be a discrete event. So that's exactly right. So I'm not writing an equation that is saying that x1 should be x prime should be related to the same x prime in a funny way. I'm saying make a discrete jump to this new value that happens to depend on the old value. So this is a perfect example of why we need an x plus that's different from a plus equals that's different from an equals. Yeah. Okay, now we try this. All right, so we get our bouncing. Now what's the story with this bouncing? It's a very, very interesting thing because if you look, there's many different ways to look at this, but there's a very geometric way to look at this. If you look at the tips that happen here, and if I happen to have a ruler, do I happen to have a ruler somewhere? Or something that looks like a ruler? So this, it's not long enough. Maybe a piece of paper might do the trick. Geometric proof, the best kind of proof since the Greeks, right? So if you kind of put a line here, you notice that these things are going in a straight line. So, there's a very well-defined point here that they're all pointing to. So what happens at this point? Ah, a string! That's the string theory. Thank you so much. Great idea. This is innovation at work. All right, so does this look like a straight line? Yeah? All right, so what's going on at this point? Thank you. Any thoughts? What's up? Yeah, there is, that's right. The half factor that we're doing here makes every jump be twice as fast. So actually, if you know something about these parabolas that are formed, the speeds are equal in magnitude at the beginning and at the end because of preservation of energy. Yeah? So then it means that every parabola at the ends has half the speed. And can you guess a relation between the heights? Just by looking at these things? Can you guess the relation between this height and this height? This says here it's 2, and then this says this is, this says it's 2.3, and this says this is 0.5 or 0.6. What's happening to the height? It's about a fourth, yeah? So if we have something where the heights, okay, now guess what's going on with the length that this thing travels? Can you guess the relation between this length or this length and this length? That it's halving. The length that you're traveling is halving. So if I'm halving the length that I'm traveling every time, how far do I go? Do you remember a guy associated with a story that sounds like this?
Yeah, actually it's chasing turtle.
Yeah, the turtle. That's right, the turtle. What's the name of the guy?
Achilles.
Another guy. Zeno's paradox. Why is this such a big deal? Well, it doesn't quite happen so easily in continuous systems, and it doesn't seem to happen in discrete systems. Where you put these two things together, you have this behavior. And what it can do is if you try to detect every single event, you're going to go into an infinite loop in a finite amount of time. So trying to simulate a finite amount of time, you're going to go into an infinite loop. This is a real shame because these kinds of simple models are extremely convenient. And when we're trying to understand things, this model of bouncing is really great. We'd like to keep it. We can do all kinds of little tricks to avoid this kind of if statement and bouncing and impact, but it's really useful. At the same time, if we use it, then we will go into an infinite loop simulating if we really want to detect every event. Now, if we zoom in this part, we know that in this particular simulation here, there's no localization. We don't try to detect the time when the event happens or the earliest time when this happens. So what happens here is actually in all of these ones, we just detect the fact that, well, it has slipped below 0. And when I was writing the model, I was telling you I'm being a little bit sloppy here. And what I'm doing is I'm writing x is less than 0 because I'm working in discrete steps and I'm not doing localization in this case. What do you think happens if I write the condition that I really want, which is hitting the ground? Any thoughts? What would happen if I replace x less than 0 as the event for detecting, the condition for detecting the event, to x equals 0? Yeah, you get over the event and it goes whew. So this is the 0 line, the blue line here, and what I have is a ball that just continues to fall through the ground. Because if I look closely at what happens when I'm crossing 0, that's not where it happens. Here we go. So at this point it's above, at this point it's below. It is never exactly at 0. So if I'm doing it equals 0. And if you're familiar with programming, which you shouldn't worry about when you're doing modeling, but if you're familiar with programming with floating point numbers, you're taught not to ever do equalities on floating point numbers, because that's usually a sign that you're doing something not quite right. So this is why I kind of cheated a little bit to be able to show you this. And in fact, this cheat is very common, that sometimes people don't think about it, yeah, to deal with these things. But the big problem with this is you then start letting the numerical methods leak into the answers that you're getting. So if you're, for example, trying to count how many times this thing bounces, you will obviously get the wrong number here, because it doesn't stop bouncing here, or it doesn't continue bouncing at this frequency here. If you go to the Zeno point, like past the Zeno point, like here, the ball is supposed to have bounced an infinite number of times. Okay, well, if you really want to know the number, you're going to have a problem because there's going to be infinity. But if you don't care about the number and you just want to know something like the ball stopped bouncing, you're not going to be able to get to that point in the simulation. Even if you don't ask any questions about the simulation, in traditional simulation methods, if you try to detect every event, you're going to go into an infinite loop. Time is going to stop. Sometimes when you study hybrid systems, formally you say, the system blocks. No, there's no progress. You can't make progress because you're kind of spinning your wheel. There's an event that happens infinitely at one point, which is you're just bouncing to zero height. Not a good thing. So it's a real shame to have things like this crop up. But it's a little bit of the price. We saw how convenient it is to model in hybrid systems. It makes a lot of things very easy. But at the same time, there are some new challenges that one has to deal with to build simulation tools, to build analysis tools for these kinds of things. So I'm going to leave it at that. There's several papers that address this in different ways for a moment. And then I will switch to talking about something else, which is these enclosures. And then we connect the two things together. So what are these enclosure things? If we zoom in on any trajectory like this, we see that we're making steps in time. And in fact, the whole idea of a line between steps is a little bit of a fake thing. If we go and say plotting, and I want the plotting to be dots, the only thing that we actually know about what's going on is these dots. And we really don't know what happens in between when we look at the results from the simulation. So in fact, if we zoom out, this actually is better than what we had before, because when we have the discontinuity, we are not trying to say that we're going to have all the values in between. We actually, when we jump, we go from a negative value down here to a positive value up here. Yeah? So is this okay? Well, especially for really precise things where we want to know if we cross a certain value, or more generally, if we want to do safety analysis. Remember, trustworthy autonomous systems is the theme for our discussion this week. If we want to do safety analysis, and we even just want to know if the system goes in a particular area or hits a particular value, we don't want to be subject to all these numerical issues. We want to know whether we really get to these values or not. Because it makes the difference between two cars crashing or passing by happily without crashing. So the basic idea that we start introducing here is this enclosure idea, and I will use a very simple, even simpler example to look at this. So another purely dynamical example, or continuous example, I'm going to say x, there's an x and there's an x prime, and maybe there's even an x double prime. So this is a kind of a simple system that gets dampened, and we'll start maybe with 1 or 10 here, and the relation could be something like x is equal to minus x prime, or it could be even minus x minus 10. Does anybody have a guess of what this system is supposed to be doing? This is a little bit like what we had in the first car, in the red car, yeah? It was trying to get to a particular speed. In this case, this is getting to a particular position. Yeah? So we can just run it and see what happens. Nothing happens. Okay. Well, that's good. That's not what I expected. We need a different initial value. We don't want to start exactly where we want to be. All right, then we get this. So this is the position, and the position starts at 0, close to 0, and then goes to something close to 10. And then this is what happens to the speed on the way, and this is what happens to the acceleration. Now the question is, for this simple system that's so well behaved, we even, it's a linear differential equation, so we even have closed form solutions for this. Are these numbers correct? If I go to this particular value, is this number going to be exactly correct? Well, the chances are, because there's so much floating point computation, even though the last 2 digits here are 701, it's very unlikely that these are the right figures. So what enclosures do, and the techniques called validated numerics, is the following. What they do is they say, well, we're not just going to remember in our calculations what the point value, or we're not going to give you just a best effort point value. We're going to do something a little bit more interesting, which is we're actually going to give you a box or a set. And what this says is, if you look at one step, we're going to give you for the whole step a lower bound and an upper bound. And furthermore, we're going to guarantee that whatever the real value is, it's going to be somewhere there. Okay? So The size of these boxes, because we look at these steps, is a little bit deceiving, but it's very useful to look closely at what's going on here. The size of the box here is mostly an artifact of the fact that the upper and lower limits are flat. If we had kind of like limits that go like a line, yeah, an envelope that's made of two lines, we could actually get by with much thinner lines here. But the internal computation is more precise than what we see, and the reason you tell that this is the case, so this box is a little bit fat here because the actual function is more like going more like this. Yeah? But if you represent the lower and the upper by just a constant, then it has to be something like this. But to get an idea of the actual precision of the computation, we can zoom in a little bit here, and you can see that it almost looks like there's just one point that these two boxes agree on. Yeah? And that is the point that's passed from one step to the next as the initial value. If we look even more closely, you see that it has a little bit more of width. Even more closely. Okay. So it's actually this distance here is the actual uncertainty about the value that we hand over as the final value from the first box as the initial value for the computation in the second box. Okay? So it actually can look a little bit less precise than what you think, than what it is, but it actually can be very precise. And in addition to giving us a computation that is guaranteed and allowing us, therefore, to do tests on things like if the value is equal to 0 and responding to them, then we're actually able to work with fairly large uncertainties. And this can be valuable by itself. So let's imagine that we don't start with 0, but we start with something like from -1 to 1. So actually this technique is able to simulate these things. And then suddenly we're able to do simulations that are working with sets. And they're doing it rigorously. So in fact, we can even have bigger sets. Let's imagine, say, we start with -5 until 5. What this one simulation is giving us is it's telling us if we start anywhere here after this particular amount of time, we will be here. So let's imagine that there's an area that's considered to be unsafe. Let's imagine that we have to jump over a wall, yeah? And the wall is only this high. Then this computation is telling us that our system, wherever we start from, following this dynamics, is guaranteed to get you over this limit at that time. Yeah? So this is actually a perfectly formal, rigorous method that allows us to prove things about our dynamics. And if we imagine vehicles going around in a city, and some places are safe and some places are unsafe, including two cars kind of being overlapping with each other. If the simulation that is using enclosures is able to show us that these things never overlap, then our cars and their controllers are safe for this particular scenario. Cool? Good. Now, this is obviously useful for a lot of things, but remember we're talking about this Xeno behavior. So how does that connect to that? Well, it's a little bit of an aside. There's a kind of a, let me kind of make a couple of remarks before we get to that. One thing that you notice here is, it is, for this particular system, kind of interesting that even if you start with a big initial set of states, you get this kind of effect here. Does anybody have an idea what this is? The fact that you might start with a very big set of initial states and then at some point have a small kind of set of possibilities for this value here and then get back to a bigger set of states? Any thoughts? Or let's think about this distance between this occurrence here and this occurrence here. Any thoughts about that? Yeah, we can think of it that way. So the fact that things get thin and then widen again, of course, this is very much connected to the fact that there's multiple dimensions and this is not a single valued kind of single dimensional state. But these are almost kind of like resonance frequencies. or natural frequencies for this particular system, where whenever you start, basically you're going to get to a certain value at a certain point, and then you go back to these things. But it's a very interesting effect that you just see from these simulations that you don't see in a single point, or you may not see very easily on a single point simulation. So there's already a sense in which we get a different picture in terms of understanding systems when we do these kinds of things. But I'm going to switch a little bit to go faster to the slides. And I'll point to a more kind of interesting aspect, or an aspect that's easier to talk about, to recognize, which is you can have these systems where you start with large uncertainty, and then after some time, you go to much less uncertainty. And you can also have like purely discrete systems where you're uncertain about the progress of the time. Maybe you have 3 nested counters, and the speed at which you're doing the computation is uncertain. Here, what we're doing is we're adding the number of times we've gone around the loop. And as we're progressing in time, the uncertainty of how far we've counted becomes high. But then once we get to this point, actually starts to go down. And here, we're completely certain about how many iterations we've gone through the loop. This is because the loop has ended. But what's really interesting is the uncertainty in this case goes up, and then here it vanishes completely. We know at this point, using this simulation, that the whole computation is done, and the answer of iterations is going to be 60 or whatever. Total number of iterations is exactly 60 at this point. And then this is what happens to the simulation of a Zeno system. So this is not just a simple kind of Zeno simulation, hybrid bouncing ball simulation. This is actually a simulation of a Zeno system where we're uncertain about how high we started. We're uncertain about the coefficient of restitution. We're actually also uncertain about the initial speed. So we're modeling the fact that we may not know exactly whether our hand was shaking when we dropped the ball. I think we're also uncertain about the exact gravitational constant here. And still we're able to generate this envelope using the enclosure technique and some extra work for the whole family of possible Zeno bouncing ball scenarios here. And we see that at this point, we're basically at rest. Yeah? What is needed for the bouncing ball, which is covered in a couple of papers that we don't have time to get into, because I think we're out of time, or very soon out of time, pretty much out of time, is essentially one more thing, which is to use the enclosures to tell us when we've reached a fixed point. So the good thing about enclosures is we know that we're working with a set, and then we can imagine whether a jump occurs. And if we consider whether a jump occurs or not and take the union of these two possibilities and the set doesn't get bigger, then we've reached a fixed point and we don't care whether a jump happens or not. And we know that this is a sound solution and we can go on to the next time step. So this is the key trick that we use for dealing with Zeno behaviors and to be able to simulate them. And enclosures are actually very useful for dealing with these kinds of behaviors. So this is just going back to the classic Zeno example. This just gives us a sense of the more precise results that we get for more precise parameters, even with really big time steps. Another thing that is good to mention in connection to discussions about probabilities and reliabilities. Here's a model of a dynamical system which says x prime is minus x3. It's a nonlinear dynamical system. And here, this is essentially the enclosure if we start from this set of possible states for both the x and the x prime. And what this is if we take a cut here and assume that there's a uniform distribution of values in the initial state, we can actually compute using enclosure methods, CDF for the values here. And what's interesting about this is, if you look at the CDF for a uniform distribution, it would be a flat line. Yeah? And because this is a nonlinear system, it actually changes the density of things. And in fact, the way this system works is that you tend to accumulate more probabilities closer to the edges. And that's reflected by this numerically computed CDF that gives you an upper and lower bound for the exact probabilities in this section. So there's a lot more to be said about this. all I want to say here is that there are very good natural connections between enclosures and working with probabilities throughout our models and computations. I'm not going to talk very much about my background. There's a slide on that that will be shared in the notes. The takeaway that I would like to suggest from this is that hybrid systems are a really great tool for modeling cyber-physical systems, and I hope that also I interested you in this particular tool that we've developed, Acumen. The main thing that hybrid systems do for us when we're modeling is to make it easier when we're thinking about things that matter to us about cyber-physical systems. And also that they help us experiment and learn about the things that we are designing. There's also things like Xeno and sliding mode or sliding effects that come up that make the simulation of hybrid systems a little bit more challenging, but there's a lot of interesting research and good progress on these areas. And I also want to mention that there's a book on the way. Springer has we got a contract with Springer for an intro to CPS book that we're supposed to finish in September. And if you're interested in a draft, I would be happy to share it with you. Just send me an email. So I hope that this will be a useful reference for these kinds of things. Thank you very much.
Thank you very much, Paddy.
Yeah.